Hey dear students, so I'm here with the next session of B2A series. In the previous session, we covered regarding magnetic force on a moving charge particle and the trajectory that it undertakes. Okay, so we covered two cases. One case was when theta is equals to 0 or 180 degree. In that case, the particle follows a straight line, and the next case was when theta becomes 90 degree. Here, theta is the angle between the velocity vector and the magnetic field vector. In the second case, when theta becomes 90 degree, we get a circular trajectory, and we did some questions regarding that. Now we are going to continue the topic, and we are going to consider a general case, that is what happens when theta is neither 0 nor 180 and nor 90 degree. So let me start, students. Let me start right away. So I'll just write the name of the topic that we were doing. So the name of the topic was magnetic force. Okay, magnetic force on a moving charged particle. Okay, so this was the topic that we were covering, and I'll just briefly tell you. So when theta was 0 or 180 degree, in this case we saw theta is the angle between velocity vector and the magnetic field vector. In this case, we get a straight line. The force is 0, and because there are no other forces that we are considering right now, so the particle continues to move in a straight line with a constant speed. Okay, in the next case, we thought about, or we considered the case when theta is 90 degree. In this case, we get a circular trajectory. Okay, so particle starts circular motion, and that too a uniform circular motion, which means the speed of the particle doesn't change. In fact, the magnetic field, the magnetic force cannot change the speed of the particle. It cannot affect because it is always perpendicular to the velocity, and therefore the power delivered by this force will be 0. So it cannot change the kinetic energy, which means it cannot change the speed. This is something that we discussed in the previous session. Now let's continue. We are going to talk about a general case. Okay, so this case will consist of these two as well as the other cases except these two. So we are going to talk about a general case. So what happens if theta is not equal to these special values? Okay, so in that case, what happens? Let's talk about that. So I'm saying that theta is not equal to 0 or 180 or 90. So whatever we are going to discuss, actually that works even for these angles. I'm not saying that theta can't be these. So when you put theta is 0 or 180 or 90, we will end up with these cases. But for other cases, this whatever we are going to discuss here will happen. So in this case, let me again draw the figure. So let's draw some magnetic field line. So let's say the magnetic field is like this. Okay, so this is how the magnetic field is. Okay, and then let's say the velocity vector of the particle is somewhat like this. So this is the particle. Let's consider a positive particle. Mass is m, charge is q, magnetic field is b, and this becomes theta. So you can see that in this particular scenario, theta is neither 0 nor 180 nor 90 degree, and we have to figure out that what will happen in this case. Let's do that. So I'll go to a blank slide where I have more space to write, and let me recreate the situation here. Let me redraw it. So we were talking about okay, instead of drawing too many arrows, let me just draw one arrow for a magnetic field. Okay, so this is a magnetic field line, and let's say the particle was somewhere here and it was having velocity in this direction, and this would be theta. Now guys, pay attention to this case. What we will do, we will break this velocity, okay, into two components, one along the magnetic field and the other perpendicular to the magnetic field. So if I do that using my knowledge of vectors, what I'm going to get is this. I'm going to get one vector in this direction. Let's call it as V parallel. Parallel means V, component of V parallel to the magnetic field, and this will become V cos theta. Okay, and let the other component be this. Okay, so this would be V perpendicular and this would be V sine theta. So we have broken the components into, like, velocity into two components, V parallel and V perpendicular. Now guys, think about this. I'll first tell you how you have to think in this case, and then using that thought process, we will come to a conclusion, and later on we will rely on our conclusion to deal with such cases. So in this case, assume if V perpendicular was not there, only V parallel was there, only V cos theta would have been there. In that case, what would have happened? Can you tell me guys? If V perpendicular wasn't there, if only V parallel was there, then this particle would continue to move in this line, in this straight line, okay, with a constant speed, and that constant speed would have been V cos theta. All right, that this would have turned into the first case that we studied, theta equal to 0 degree. Now suppose what if this is not there, like only this component is present, then what would happen? So you will conclude, I hope that magnetic field is in this direction, velocity is in upward direction, this v perpendicular, so it will experience an inward force, and we know that it has to be circular motion now, because if this is not there, only this is present, then we are talking about the second case now, theta equal to 90 degree. Okay, so the force is inward, that means the center of the circle has to be inwards. Okay, which means that just if I start considering this as x-axis, let's say this as y-axis, and let's say this as z-axis. So the center will lie somewhere on the negative z-axis, and the particle will start executing circular motion, somewhat like this. The particle will start executing circular motion like this. Are you able to see? If only v perpendicular is present, then the particle will execute circular motion. Okay, the center will be somewhere on the z-axis. Okay, and because of this v cos theta, the particle was supposed to travel like this. So when you superimpose both the things, like both the things happen together, then what happens? The particle starts executing circular motion, and at the same time it is traveling parallel to x-axis in this case. In general, we can say it will travel parallel to the magnetic field direction. So we get the shape of a spring. How you draw a spring? Okay, we get that shape. This shape is called a helix. Okay, this shape is called a helix. Okay, this is a helical shape that we are going to get. So in this case, what we see is a helix. Okay, now there are few points that we have to keep in mind, but before that, let me try to make it very clear to you that what are we trying to draw, because helix is a three-dimensional figure. So drawing it in 2D, obviously, it will take you guys some kind of imagination to imagine what kind of shape we are drawing. Okay, so if an observer is looking from here, what does this observer see? So let's try to think about this, that if an observer is looking from here, then what will he see? So guys, let's say if I am looking from here, which axis do you see do you imagine I will see going upward? If I am looking from here, okay, that is the coordinate axis, then which axis will I see going upward? Now if your answer to my question is y-axis, then you are absolutely correct. Okay, then you are absolutely correct. Now let me go back to the previous. Now if I'm looking from here, then which axis do you think will be to my left? In this direction, which axis will be there? Now if your answer is z-axis, then also you are correct. Okay, then also you are correct. And from here, if I talk about x-axis, so x-axis is coming and entering directly into my eye. Okay, I'm viewing from x-axis, so it is directly entering into my eye. So in this diagram, I will draw x-axis as a dot. I hope you remember, I told you this in the previous session, that any direction going into the screen is indicated by a cross, and any direction coming out of the screen is indicated by a dot. So we will see x-axis as a dot. Now, okay, let's go back here. Let's talk about two velocity components. So the v sine theta component in this figure, it would be drawn like this. So this was the initial velocity v sine theta. Let me just write v perpendicular. Okay, and v cos theta would be along x-axis. So I will draw v cos theta as a dot. Okay, so v cos theta is coming directly towards me. Not only that, if I have to think about the magnetic field lines, so in this diagram, how are we going to draw the magnetic field lines? Are you going to draw dots? Are you going to draw dots for magnetic field line? Think about this, because from where I am drawing this view, magnetic field lines are coming directly towards me. So I perceive them to be coming out of the screen in this perspective, in this view. Okay, they appear to be coming out of the screen to me. So I am going to draw magnetic field lines as dots. Okay, now see this. Magnetic field is outward, v perpendicular is upward, so the force will be along, it will the force will be along negative z. Okay, so the particle will start executing circular motion like this. So this is how the particle will start, and then it will finish the circular motion like this. Are you getting it, everyone? I don't think I've drawn a good circle. Let me try again. Okay, let me try again. This doesn't look like a very good figure. Okay. Okay, something like this, and this is negative z axis, the center is somewhere here. Okay, the center is somewhere here, and I hope you keep this in mind that the particle is moving not only in a circle, but it is coming outward also. So it is coming towards the camera in this view, which of course I cannot draw here. So this is the kind of thing. Now, if we talk about the other parameters, like what are the parameters? Like, for example, what is the radius of this circle that we are going to witness? Okay. So the radius of this circle, think about this. You know, in the second case that we did in the previous session, we wrote radius as mv by qb, and here that v would be v perpendicular. Okay, this was v perpendicular, this was v perpendicular. So here the radius would be mv perpendicular by qb. In other words, it would be mv sine theta by qb. Okay, and then if we have to find out the angular velocity, okay, then it would be v perpendicular by r. Ultimately it will turn into qb by m, and the time period will also become 2 pi m by qb. Time period will be given by 2 pi by omega, so it will become 2 pi m by qb. So you can see that the omega, the angular velocity, and the time period, they are not dependent. They are not dependent on the speed with which you have projected it. They are not dependent on that. Okay. Now, so this r will be called the radius of the helix, and this in this particular case, it is like we call this like the spring. If you imagine spring, you would say that spring is like a curve drawn on the surface of a cylinder. Imagine this. If this is a circular cylinder, you wrap around a thread like that, then that thread will take the shape of a spring. So spring is a curve which we can assume to be drawn on the surface of a cylinder, and the radius of that cylinder is called the radius of the helix. So that is what we have written here. Okay, this is the radius of the helix. Okay, now there is another very important thing regarding a helix, and that is the distance between two consecutive threads. Okay, this is called the pitch of the helix. Okay, you may have heard this term before, pitch of helix. So this pitch word is used in terms of when we have to talk about a screw. Okay, in a screw also the threads are like the shape of a spring. Only if you have seen a screw, you know that the shape of the thread is like it is like a helix only, and pitch is the distance between two consecutive threads. Okay, so how do we calculate pitch? So can we say that pitch would be the distance covered by the particle in one rotation, like as it completes one circle, and in this direction the particle is traveling with a constant speed of v cos theta. So we should be able to write the pitch of helix as v parallel into the time period. So it will become v cos theta into 2 pi m by qb. So this will be equal to the pitch of the helix. Okay, now there is one important thing here to keep in mind, and that is the axis of the helix. The axis of the helix will coincide with the direction of magnetic field. So keep that in mind, that the axis of the helix, it coincides with the direction of magnetic field. Alright guys, so I hope this part is clear to everyone. Let me give you a situation. Okay, let me give you a situation and you try to figure out that what will happen in this case. Okay, there's one more. There are a few more things that we can do in this case. If I ask you about how much is this angle, what will you say, everyone? Like if I consider that the location of particle here, this instant was t equal to 0, then in time t, can I say that the particle will have covered an angle of omega t? Okay, because if we are in a position to say that, then we can readily write the coordinates of the particle. Suppose we want to write the various coordinates of the particle. Okay, so understand this. The particle is here after time t. So this height will represent the y coordinate of the particle, and this height is same as this height, and I can write this height using this r and using this angle. So the y coordinate of the particle will be r sine omega t. R is mv. Mv sine theta by qb, and then sine of qb by m into t. So that becomes the y coordinate. Similarly, if you want to write the z coordinate, notice that this is the z coordinate, and of course it is on the negative side. So if we want, we can write the z coordinate as minus of this length. And how much is this length? This is capital R minus r cos theta. So this is capital R minus r cos theta is actually omega t here. So this will become minus mv sine theta by qb into 1 minus cos of qb by m into t. Just have a look at this. So this is z. And what about the x coordinate? Now x coordinate is pretty simple. In the particle is traveling along x direction with a constant velocity of v cos theta. So it would be v cos theta into time. So we have written the x coordinate, we have written the y coordinate, we have written the z coordinate, which also means that we are now in a position to write position vector as a function of time. We will write xi cap plus y j cap plus z k cap. Okay, so x can be substituted from here. Okay, y can be substituted from here, and z can be substituted from here. So we obtain r vector as a function of time. Now suppose if you have been asked to write velocity vector as a function of time, you can simply differentiate this to get velocity vector as a function of time. So now you are in a position to write the velocity vector. Remember, the speed is not changing, but the velocity is changing. So at different times, the particle will have different velocity. And if you want to write the velocity vector, then you can just differentiate this. This will give you the velocity vector. Okay, and then if you want to write the acceleration vector, you can differentiate it once again. Although acceleration can also be written by considering force upon mass. We know how much the force is there. So force upon mass will also give us the acceleration. So guys, this is how we do the math related to this situation. Okay, now let me take up an example. Let me just take up a quick example. So suppose we have been given magnetic field as B naught j cap, and suppose the initial velocity is given as V1 I cap plus V2 j cap. So this is how the velocity is given. We've been given that the particle's mass is m and charge is q, and particle was at origin at t equal to 0. Okay, particle was at origin at t equal to 0. So all this information has been given to us. All this information has been given to us. And what does the question asks us? Let's say question asks us that at what time particle hits y equal to L plane. Okay, now let's first solve this, then we may add some parts to it, but first let's try to solve this. Okay, now let's ignore what has been asked. Let's first analyze the situation. So according to the information given to us, magnetic field is in the j direction. So to just start thinking about this, let me draw the coordinate axis. That axis is coming out of the screen, and according to the question, the magnetic field is along j. Okay, so all right, I will draw. So guys, it's not that the first thing that you will draw will be helpful, but you can start from what you have practiced. We generally consider x-axis here, y-axis here, so I'm starting from that figure. Later on, if I realize that some other perspective may be more useful to me for solving the question, I will adopt that perspective. So I'm just trying to get a hold of the situation right now. Now the question says that the particle was at the origin at t equal to 0. Well, then in that case, I will say that okay, the particle is here, and the particle had velocity components v1 and v2. So we will assume that in this direction particle had a velocity of v1, and in this direction the particle has a velocity of v2. Okay, now you can clearly see that we have already been given the v perpendicular and the v parallel. V1 is v perpendicular because it is perpendicular to the magnetic field lines, and v2 is v parallel. Okay, and now guys, if I think of this, magnetic field is in upward direction, velocity is in this direction, so positive particle will experience a force out of the screen. So the z, the center of the circle will lie on the z axis. So this particle would have rotated like this if there was no v2. If there was no v2, it would have rotated like this, but because of the presence of v2, it will rotate and it will go up also. Are you able to imagine? So let me draw it now. Okay, so this particle will, it would have made circular motion like this. Okay, it would have made, but it's actually it's actually going like this, such that the projection is this green circle. Do you understand what the projection means? Like if someone is looking from the top, then that person would see the green circle. Okay, so let me draw this view also. So now I know that this view will be more helpful to me. Okay, this view, in fact, the question can be solved here. Like as far as this question is concerned, we've already solved it. How? See, in this direction, the particle is traveling with a constant speed. And if we are talking about a plane which is y equal to L, so y equal to L would mean plane perpendicular to y axis. So if this is x-axis, this is y-axis, y equal to L plane would mean something like this, you know. Y equal to L would mean, yeah. See, this point is 0, 0, 0, L 0. Okay, this point is. So, the time that this particle takes to reach this plane is very simple. It is L. You know, this distance will be L, this distance. Okay, so L by V2 is the time. So, we have already got the answer to the previous question. But let's say the question asks us, okay, tell me the coordinates of the point where the particle hits this plane. You know, so particle is going like this, and let's say it strikes somewhere here. Now, what are the coordinates of this point? Suppose next question is, what are the coordinates? So time we have found, but if we want to look for the coordinates, let me show what to do. So suppose you are looking from the top. If you are looking from the top, then again let's try to understand. I'm looking from the top. Okay, I'm looking from the top. The particle is coming towards me. On this side, it's x-axis. Towards me is the y-axis, and z-axis is going like this. Okay, so what I will draw now. See, this is x-axis. This is z-axis, and y-axis is the dot. And okay, and the particle was here. Particle had a velocity along x, which is v1, and the particle had a velocity along j, which is v2. And again, the magnetic field lines are entering into my eye. So I will draw dots. Okay, so this is magnetic field lines. Okay, and I now know that, you know, if there would be no v parallel, then the circle that we would have got would be like this. It would have been a circle like this, and it is coming like this. So the particle started moving like this. So in time t, the particle would cover an angle like this. This is omega t, and now I am very clear that the x coordinate of the particle, okay, this will become the x coordinate of the particle. So the x coordinate of the particle would be r into sine omega t. And how much is r? R is m into v perpendicular, which is v1. Okay, yeah, that is r. So it becomes m v1 by qb naught sine of qb by m into t. This is x coordinate. Now what about the z coordinate? Okay, what about the z coordinate? So this is z coordinate. Okay, and it's on the positive side. So z coordinate would be r minus r cos omega t. So it will become m v1 by qb naught into 1 minus cos of qb by m into t. This is z coordinate. Okay, and what about the y coordinate? Y coordinate would simply be v2 into t. Okay, so we have got the three coordinates. You know the time at which we want to know the x and the z coordinate. Just put the value of t here and here. Not here, in these two. In these two equations, you put the value of t and you will get the x and z coordinate as well. Y coordinate is definitely L, because that's what we are solving for. Okay, so like this you can get the coordinates also. So this is how we deal with this case, guys, the helical motion case. Okay, now we will move to the next topic, which is force on a current carrying wire. Okay, so let me write the topic name. So we are now going to talk about magnetic force on a current carrying wire. Okay, now guys, let's understand what we are trying to do. So we first calculated force on a moving charge particle. So one particle was moving, we wrote the expression of force on that, and based on that force, the particle can undertake different trajectory, the straight line, circle, or helix. Okay, we studied about that. Now what if instead of one particle we have a stream of particles? You know, there are many particles which are traveling in a magnetic field, so all of those particles will experience a force. Okay, and that will amount to a certain amount of force. Now a stream of particle moving is electric current. So if I want to extrapolate my concept that I just learned in the previous section, that is magnetic force on a moving charge particle, now I want to talk about a system of particles. I want to talk about many particles. Then we are talking about current, and therefore we are now discussing magnetic force on a current carrying wire. I hope you understand that how the two are related. In the previous section we talked about one particle. Now we are going to talk about a group of particles which are moving with the same speed, the drift speed. All right, and we want to know that what will be the total value of force on that. Okay, so let us consider case wise. Okay, let us consider case wise. So case one, maybe we can name it later. Let me just try to explain the situation first to you guys. Okay, so case one is this. Let's say we have a magnetic field. Let's say somewhat like this. Okay, so into the screen. These crosses indicate a magnetic field into the screen. Okay, so let's say this is the scenario. Okay, and now let's say there is a rod, wire, whatever you want to imagine, it which some current is flowing. I current is flowing. Okay, let the length of this be L. Let the cross section area be A. Okay, so when I say that the current is flowing through wire, what is actually happening is that the electrons in this wire are moving in the opposite direction. So the reality is this, that there are free electrons in this wire and they are moving back. Okay, and the average speed with which they move is called the drift speed. Okay, so what is happening is that every electron, okay, is experiencing a magnetic force. Magnetic field is inward, velocity is in this direction. Electrons are negative particles, so they will experience a force towards the back of the palm. Okay, so all these electrons are experiencing a force which will be given by charge of the electron drift speed into the magnetic field. Okay, all right, so whatever number of electrons are present in this wire, okay, all of those electrons are experiencing this force, and when we add all these force, let's say this is force on one electron, so force on one electron plus force on second electron plus force on third electron and so on. When we do this, okay, I'm not doing the math here, I'm giving you the direct relationship. When we do this, we get the net force on the wire. Okay, we get net force on the wire, and that comes out to be BIL. Okay, so this is the force acting on a current carrying wire. Now, right now let's write this, and remember that this was case one. Okay, I'll talk about more cases. So this was case one. Okay, BIL. Okay, where B is the magnetic field, I is the current flowing through the wire, and L is the length of the wire. Now, what is case 2? Let me show you what is case 2. So, suppose in a situation magnetic field lines are like this. Okay, suppose in a situation magnetic field lines are like this. Okay, and there is again a current carrying rod. I current like this and I current, and again if the current is flowing like this, then the electrons are definitely moving in the opposite direction. Now guys, can you think about how much force is acting on one electron? The velocity of the electron is parallel to the magnetic field, so the force on individual electron will be zero. Here the force on one electron will be zero, implying F1 plus F2 and so on will be zero, and therefore the net force will be. Now guys, do you see the difference between the two situations? In case 1, what did we do, and in case 2, what did we do? Okay, in case 1, the length of the rod was perpendicular to the magnetic field, and here the rod was parallel to the magnetic field. Okay, so if I want to talk about a general case, now know that what will happen. Okay, so if I want to talk about a general case, now what would a general case look like? So suppose there is magnetic field like this. Okay, there is magnetic field like this, and there is a current carrying conductor like this. Okay, and this angle is theta. So you see that this time the rod is neither perpendicular nor parallel. Okay, and of course the electrons would be moving along the rod like this. Okay, in this case, if you have to write the force on the rod, okay, what you have to do or what you can do is that you can take components of the rod. One component of the rod parallel to the magnetic field. Okay, so this would be L cos theta, and the other component of the rod along perpendicular to the magnetic field. So this would be L sine theta. So this is one way of thinking, that you break the length of the rod into two parts. Okay. And now if current would have been only in this wire, so magnetic field is there, current is upward, force would have been inward. So the force on the rod, okay, the force on this rod will be inwards. Therefore, I'm drawing a cross, and that force would be B I L sine theta. Now that is one way of thinking, where we are breaking the length into two parts. There is an alternative thought also. The alternative thought is like this. Let me redraw the figure. So suppose magnetic field is like this. And the current carrying rod is like this. Okay. Now the alternative thought is that instead of taking the components of length, you take the components of magnetic field. So magnetic field is in this direction. Okay, let's say B, this angle is theta. So in this direction, that is parallel to the rod, the component is B cos theta, and perpendicular to the rod, the component is B sine theta. So we'll remove this now because we have broken it into two parts. Now B cos theta will not play any role in the magnetic force, whereas B sine theta will play a role. And again, the direction is coming to be inwards. So now you will write force as sine theta. B sine theta into L into I. So here you took the component of length. Okay, so this L sine theta, the entire B, then I, then L sine theta, and here you took the component of B. So final expression remains the same. The direction of force also remains the same. Only that your way of thought is different now. So whichever way suits you, you can go with that. And it may also happen that in some questions, this way will suit you better, and in some questions, this way of thought will suit you better. Okay, so that is how we can write force, magnetic force on a straight current carrying wire. So if I check all the cases, case 2, case 3, case 4, case 1, 2, 3. So in case 1, L was perpendicular, in case 2, L was 0, in case 3, like L was parallel, and here it was a general situation. Okay, so if I have to summarize a general formula, like, if let's talk about a small length DL. Okay, a small length DL in which current is there. You remember current element? Okay, now and there is a magnetic field, let's say. So how do we write force on this? Like, is there any formula which can take care of all the three cases? Okay, so you see that if you write force dF vector as I dl cross B, this takes care of all the three cases, magnitude wise as well as direction wise. Everything is covered here. So dl cross B will be into the screen, and you see that I dl B sine theta will be. So this is the expression that we are looking for. So all the three previous cases are covered here. So this is how we write force on a small current carrying element. Okay. Now, are there any questions that we can practice here on this topic? So yes, guys, I'll cover some questions on this, and I will extend the same topic in my next lecture. So guys, I hope you were able to understand whatever I've explained today. And just in case you were not able to understand, or you found my speed to be a bit higher, in that case, guys, please keep in mind that my speed is in your control. You can always slow down the video, and then you can watch it again. Also, you can pause the video at times. If I'm speaking something and if you did not get hold of what I said, then you can pause the video, go over that statement again, think about it, and then you can continue the video. So if I'm making a 30-minute video, I don't expect you guys to watch that in the 30 minutes only. When you watch it in solitude and you try to understand each and everything out of that lecture, it will take approximately 50 to 60 minutes for you guys to grasp the entire idea that I shared in 30 minutes. I want to keep it terse, I want to keep it short, so that your time is not spent in going through the session, that what happened, and then you can play the session at your own comfortable speed. And you should do that, and then you have to make notes of whatever I've taught. And if you are studying that way, then you will find that whatever you are learning, it is helpful to you in problem solving as well. Now guys, I hope you guys are already aware of the NSEJS examination. And if not, Nidhi ma'am has done a lot of videos on this examination, detailing this examination. Go and see those videos so that you are become aware of that examination. And you must prepare for this examination. Like, you are an NSEJS scholar, so preparing for this examination will not take too much of your time. You have to just prepare mathematics additionally. Everything else you are preparing within the NSEJS batch only. All right, and if you want to prepare for this batch, then guys, there is this exam. Then there is a batch that we have launched. You can join that batch and you can prepare for it. Okay, these are the the details. I'm pretty sure that you guys have already seen this. Okay, so just in case if you want to join that batch, the price is this, but we are not enrolling at this price. We are enrolling at a discounted price of 8,000. So if you want to join this batch, there is a link in the description of this session. You can click on that link and you can join. Okay, and guys, do not forget to share, like, and subscribe. Oh, something is wrong. Huh? Anyways, anyways, so like the sessions, share it with your friends, and definitely subscribe this channel, everyone. You'll see me in the next session very soon. Take care, everyone. Bye bye.